This video explains the example of finding the moment capacity using first principle methods for 600 millimeter depth beam by 350 millimeter wide doubly reinforced section shown in the figure. Characteristic strength of the concrete is 32 megapascals. Cover to R10 stirrups. So this is the stirrups is 30 millimeter to the top and the side. So at the bottom, and side is 30 millimeters and at 60 millimeters at the top. Now we are working in the Newton millimeter and megapascals throughout. Now first of all, ASC, it's given the N28 bar. There are 2 bars, so we can use the Rio tables and we find it out area of top reinforcement, which are this one, compression reinforcement. That area is given in the Rio table, 2 and 28. So here we have a 28 and 2 bars, so we should take 1232 millimeter square. So that is 1232 millimeter square. Now this is the depth. DSC is the depth of the top reinforcement from the top of the beam. So the cover is 60 millimeters given here, 60 millimeters plus 10 millimeter of stirrups plus 28 is the diameter of the reinforcement. So 28 divided by 2, it gives us 84 millimeters. So depth of the top reinforcement from the top of the beam is 84 millimeter. Now area of the bottom reinforcement, AST, which is a tensile reinforcement, there have a 8 and 24 bars. So again we can use the Rio tables, and for N24 bar and there are 8 bars, so we have a area of 3616 millimeter square that is given here. So that is 3616 millimeter square. Now small d is nothing but the depth from this 32 millimeter space bar from the center to the top of the beam. So that is 600 millimeters is the depth. So for example here for the sections we have a that is 600 millimeters. So that 600 millimeters, take away 30, that is cover here, 30 millimeters is a cover that is given here, bottom cover. Take away 10 millimeters of stirrups, take away 24 millimeter of this reinforcement, minus 32 divided by 2, that is the space bars, is 522. Please note in here these sections we are not considering into the design. This cross section we are just removing from our design, therefore we are just taking into in our design. We are not designing for 600, we are designing for 528 millimeters, because this cover is just to protect the reinforcement from the external environment, for example from the corrosion. Now we need to calculate few parameters before we go into the great detail of the analysis. First we need to get the alpha 2 value, and now this alpha 2 value is taken from Australian standard clause 8.1.3. now in AS page number 110, and we have this clause 8.1.3. we have a alpha 2 value of 0.85 minus 0.0015 FC dash. FC dash is 32 given in the questions. FC dash is 32 megapascals given in the questions. Simplification gives 0.802. we just need to check whether it's greater than 0.67. if it is there, it is okay. Gamma value is also given on the same page. On the page 110 we can see that page 110 of AS360 we have a gamma value of 0.97 minus 0.025 FC dash. Substitute again the FC value 32, it gives us 0.89, which is greater than 0.67, so that is okay. Now we first step is to calculate the DN. I have prepared the analysis steps, design steps, because it's a quite long procedure, so I prepared those analysis steps. Now these analysis steps are given here. That is a design procedure for doubly reinforced beam. And for first principles we need to calculate DN first, and then we need to calculate the strain in the top reinforcement, and then we need to do the few checks. So this is the procedures we are going to follow. So let's calculate the DN value. Now there is an equations in the previous video. In the theory we take the calculation for DN value. If you remember that one, in the previous video we used these DN equations. We can straight away use these DN equations, substitute all the values, and we can find this one. Alternatively, we can also find using 3 different component, and for equilibrium we can find a DN value. Now first assumptions we make that top reinforcement, they are at the yield, they should yield before the concrete, so it should fail first. So that's what yielding is. This is a condition in the design. We never get a conditions where yielding is not happens. We must yield that compression force, compression reinforcement. Now this CS is the compression force in the top reinforcement, is calculated this force equal to area times stress. Area is 1232. We get this area of top reinforcement 1232 millimeter square. That is here times the yield strength is 500 megapascals. We are using this Rio tables. In that Rio tables we generally have these 500 megapascals. Give 606 times 10 to the power 3 newtons. Now this is the compression force in the concrete, which is alpha 2 FC dash. This is the stress times the area gamma DNB. Alpha 2 we calculated 0.802 times the FC dash value 32, gamma value 0.89 we calculated here, and DN we need to calculate times the width 350 given in the questions. That width is 350 given in the questions. That's given 7994.336 DN. Now tensile force, that is the bottom reinforcement ASTFY, area times stress. Bottom reinforcement 3616 area, that we just check it, just done it first in the previous steps, times 500 give us 1808 times 10 to the power 3 newtons. Now the cross section must be in the force equilibrium. So compression force positive, tensile force negative, equal to 0. We substitute all the values, 7994 for CS, for CC. CS is 616 times 10 to the power 3, and we substitute the value for T. And if you simplify that one, we can find the DN we can alternatively find DN 149 millimeters. Now that is step number 1. Now if I go back here, we calculate this DN value, very straightforward, simple procedures. Now after calculating the DN, we need to check, this is very important here, we need to check whether, because we made the assumptions here, that top reinforcement should be yield. So we need to make sure that this ESC top reinforcement should be greater than ESY, right? So in here we have a equation to calculate the strain. In the previous video, in the theory we use these equations ESC. So if I simplify here, I should get ESC equal to 0.03 times dN minus DSC on dN. So that is the equations I write. That is the equation I write here. Now we substitute the value 0.03 times dN 149, that we just calculated in here 149 millimeters. Take away 84 DSC. Now that DSC is we calculated here. What is DSC? DSC 84 millimeter. DSC is nothing but that is the from the center of the top reinforcement to the top of the beam, 84 millimeter that we calculated. Substitute 84 over 149. That is 0.013. That is less than ESY. What is ESY? ESY is nothing but FSY on ES, which is, let's say, 500 over 200,000, that is given as 0.025. So obviously 0.0035 is less than, we need the value which is greater than 0.025. So what happened here? This DN is not correct. 149 millimeter DN is not correct because our steel is not at yielding. Now this is the typical case. As I mentioned, we have two cases when you have ESC is greater than ESY in the theory, or if you have a ESY which is less than ESY because the steel is not yielding, then we need to follow these steps that I mentioned. Now here we have a design procedures here where I can tell you that we calculate this one, and this check is is comes here. This is ESC is less than ESY, so we need to follow these these few steps here. Next video will explain how we can going to follow these procedures. Thank you very much.